I have the pleasure to announce Remko Uijlenhoet from Wageningen University. And even though he's also an expert on radar QPE, he will tell us a little bit about opportunistic sensing of rainfall, so other sensors that typically we wouldn't think of when talking about QPE. And in principle, the screen is yours, Remko.
Thank you very much, Christian, for organizing this conference together with your colleagues and also for introducing me. So indeed, we're going to slightly change gears here as announced by Christian. This presentation will be dealing with opportunistic sensing of rainfall. So rather than the dedicated sensors that we have been seeing in the previous presentations, notably weather radar, we're going to move to opportunistic sensors, and opportunistic sensors are basically sensors made of infrastructure that was not designed to measure rainfall. And I'm going to give you a couple of examples of that, but that will become clear in the remainder of this presentation. So one example of a dedicated sensor that is being used operationally for rainfall monitoring, obviously, are sensors on board of satellites. And we all know that they can provide very valuable information for hydrological and meteorological applications, covering the continents as well as the oceans. But of course, they are indirect measurements. So in general, we need ground validation on the one hand, and we also need sensors on the ground in order to be able to develop rainfall retrieval algorithms. A second type of sensor that we are using a lot in meteorology and hydrology are weather radars, and we've already seen a number of presentations dealing with various aspects of rainfall retrieval using a weather radar today. Of course, a disadvantage of weather radar is that the global coverage is far from complete. As you can see on this image, the coverage over Northern America, Europe, and parts of Southeast Asia is still reasonable, but for other parts of the continents, as well as the oceans, obviously, the coverage is far from complete. So in order to be able to obtain global rainfall imagery, at least on a continental basis, weather radars cannot fill this gap either. And then, of course, we have our classical rain gauges organized typically in networks. But as a paper published by the organizing group a number of years ago has shown, actually the number of reporting rain gauges worldwide is slowly but surely declining, as can be seen on the right-hand side of this picture. So these are basically numbers of gauges of which available information is accessible through the internet, basically online. And as you can see, that is slowly but surely decreasing. Now, at the same time, what we have been witnessing over the past decades is a revolution when it comes to mobile telecommunications. This picture on the left-hand side already shows you that in 2013, the number of mobile devices used worldwide was equal more or less to the number of citizens, number of inhabitants of our planet. And that has only been increasing over the past years. Obviously, there are significant differences comparing one continent to the other. But this graph basically shows you that there is infrastructure developed for mobile telecommunications that in principle could be employed for environmental monitoring and in particular rainfall monitoring, which is what we're interested in today. So basically what I'm saying here is that as a complement to dedicated sensors such as rain gauges, as shown here on the left-hand side, or weather radar or satellites, there is definitely room for opportunistic sensors to complete the picture locally in urban areas as well as globally, in particular in the global south. So one aspect that we're going to discuss today is the potential use of microwave links from cellular communication networks for rainfall monitoring. We're going to quickly show a result concerning the use of smartphones as an environmental sensor. And finally, we're going to take a closer look at the potential of citizen science, in particular personal weather stations for hydrologic science and applications. Now, it's well known if you compare basically radar, which we have seen already during the previous presentations, with microwave links, that there are some differences when it comes to the relationship between specific attenuation and rainfall rate. And whereas attenuation is a nuisance in general for rainfall retrieval using weather radars, it is actually the basic principle of rainfall retrieval using microwave links. And in general, the relationship, as is based on electromagnetic scattering theory between rain rate and specific attenuation, takes the form of a power law, as is shown on the upper right-hand side of the screen, where capital R indicates rain rate and the small k indicates specific attenuation in decibels per kilometer. And what is shown here are basically the variations of the prefactor A and the exponent B as a function of the radio frequency on the horizontal axis. And in particular, the upper right-hand panel shows you the dependence of the exponent B as a function of the employed radio frequency. And what you can see here is that for frequencies around 30 gigahertz, the relationship between rain rate, capital R, and specific attenuation, small k, becomes nearly linear because the B, the exponent of the power law, becomes about 1. And that basically indicates, first of all, that the relationship between R and K becomes nearly linear, but also that the scatter that you can expect in this relationship induced by variations in the particle size distribution, the drop size distribution, is going to be very small. And that is indicated on the lower right-hand side. And you can compare this to the scatter plot on the lower left-hand side for a typical radar frequency, in this case, X-band. You see, first of all, a much more linear relationship for 30 gigahertz, and secondly, much less scatter. Now, by surprise, the typical frequency employed by mobile network operators in their second, third, and fourth generation networks is typically around 20 to 30 gigahertz, which indicates that potentially microwave links from such networks could be used as path average rain gauges. And that is indeed the case, has been shown already by a number of groups around the world. Here I'm showing you an example from the city center of Amsterdam, lower right-hand side, the typical circular canal structure with one particular microwave link from a mobile network operator with whom we have been collaborating fruitfully for the past decade or so. And what you can see on the upper left-hand side of this screen is basically the time evolution of received signal level, minimum and maximum per 15 minutes, as compared to rainfall rate. Rainfall rate indicated in the gray line, basically estimated from gauge-adjusted radar. And what you can see is that basically whenever it rains, there is a significant attenuation, a drop in the received signal level. And using the power law relationship derived from electromagnetic scattering theory, as shown on the previous slide, we can basically employ these attenuations, divide them by the length of the microwave link path to obtain an estimate of specific attenuation due to rainfall, and then convert that to rainfall rate, which is what we did on the lower left-hand side in terms of the intensities, and the panel in the middle on the lower side in terms of rainfall accumulations. And what you can see here is that indeed microwave links, after careful quality control, can be employed as path average rain gauges. Now, obviously, if you can do this for one single link, You can do this for many individual links. And that, of course, is a definitely very nice asset. On this particular slide, you see on the left-hand side a rainfall field obtained from about 2,500 microwave links over the Netherlands from a cellular communication network of one mobile network operator. And on the right-hand side, the image that can be obtained from basically a gauge-adjusted radar using 2 weather radars, about 35 automatic rain gauges and 350 manual rain gauges. And what you can very clearly see here is that there is a very close correspondence between the two. And if I would have been able to show you the video corresponding to this event, you would have seen that also the space-time dynamics of the event is really nicely captured, thus showing you the potential of this technique. Now, obviously, in the Netherlands, we already have, as in large parts of the Western world, excellent dedicated infrastructure by means of rain gauges and weather radars. But in large parts of the world, that is not the case. Even though in those parts of the world, people are more and more using their cellular devices. So this goes to show that also in South America, in parts of Africa and parts of Asia, there is potential for opportunistic rainfall monitoring through the use of cellular communication networks. And those areas are also typically densely populated areas. Now, this shows you an example of a training school that we gave in collaboration with German and French colleagues a number of years ago in Africa, Western Africa, basically demonstrating the potential of this technique both to meteorologists and hydrologists from operational services, as well as engineers from mobile network operators. And in the past couple of years, through a collaboration with the GSM Association, we've been able to obtain access to microwave link data from cellular communication networks in several countries, notably in Nigeria, Africa. And the example over here is an example for the capital of Nigeria, Lagos, which is basically the biggest urban area on the African continent with over 20 million inhabitants. But what's more, this urban area has a very dense microwave link network consisting of about 8,500 microwave links, which we have employed using the same algorithm as before for the Dutch data. And again, we've been able to obtain some really nice rainfall estimates using the cellular infrastructure. So this is an example of using existing infrastructure developed for mobile cellular communications that we have used opportunistically for rainfall estimation. And the next two presentations will deal with this technique in more detail. Now, another example that I'm not going to dwell on too much because it's not the main topic of this conference is the use of smartphones for inner city urban air temperature estimation, which we have been able to show through a collaboration with Open Signal in London. And this shows you on the lower right-hand side a comparison of temperature estimates using thousands of smartphone battery temperature readings for the city center of London as compared to a dedicated official UK Met Office station at London City Airport. Again, showing the potential of opportunistic sensors, in this case not for rainfall estimation, but for temperature estimation. But of course, that is not the main topic of this conference. So let's move on to a third example of a opportunistic environmental sensor, and that is the personal weather station. Now, if you realize that our National Meteorological Service in the Netherlands, KNMI, operates exactly 0 rain gauges in our capital, Amsterdam, the closest rain gauge is actually at Schiphol Airport, just south of the city. And if you realize at the same time that there are dozens of owners of personal weather stations in the city of Amsterdam, which apart from temperature and humidity also have tipping bucket rain gauges installed with them, you can clearly see the potential of citizen science for hydrology and meteorology. And one of our PhD candidates has been investigating the potential of these tipping buckets from personal weather stations in more detail. And basically, to get to know a little bit more about the quality of these sensors, we have acquired a couple of them and installed them close to, in the vicinity of, an official KNMI rain gauge in order to learn more of the quality of these sensors. And basically, if you take a look at the publications related to this work, you can see that after careful quality control, these personal weather stations actually provide valuable information on the spatial and temporal variability of rainfall, both over an urban area such as the Dutch capital of Amsterdam, as well as nationwide. And actually, currently, we're in the process of, in collaboration with one manufacturer of such personal weather stations, acquire data for an even larger part of the European continent to investigate the potential at that particular scale. And unfortunately, I'm not able to show you the movie here because my full screen PowerPoint presentation is not showing on this video system. But I will upload my presentation later on and you will be able to see it offline. Indeed, you can acquire a very nice correspondence between gauge-adjusted radar on the one hand and personal weather stations on the other hand, showing you by means of a third example the potential of opportunistic sensing for space-time rainfall information and for environmental monitoring in general. So basically, what I'm saying is that in addition to the dedicated sensors, which are crucial and important and should be there to stay, let that be very clear, and dedicated sensors are then the rain gauges, the weather radars, and the satellites, obviously, that we have been already talking about during the QPE sessions earlier today. There is potential for opportunistic sensing, for environmental monitoring in general, and for precipitation monitoring in particular. And two examples that are really relevant for rainfall monitoring are microwave links from cellular communication networks and personal weather stations with their tipping bucket rain gauges. Obviously, this leads to a number of conclusions and observations, namely that opportunistic sensors could be really nice complements to dedicated sensor networks. I'm not at all claiming that they should replace dedicated sensor networks, but they can complement them, for instance, in densely populated urban areas, as well as parts of the world where the density of dedicated sensor networks is much lower. And what's more, the ongoing cellular communication revolution, and I'm talking about the fifth generation cellular communication and beyond, using also other frequencies, provides an enormous potential for hydrologic and meteorological monitoring. And I believe the next presentation is also going to pay attention to that. What we should realize, on the other hand, is that these data are being acquired through infrastructure that is not owned and operated by public organizations. So that basically implies that real-time data access from these networks requires business models for, in this case, mobile network operators. That is something that we need to think about more and that we are working on together with our partners in the European Commercial Microwave Link Consortium, of which the GSM Association and several microwave link manufacturers are part. And finally, I believe that a paradigm shift is required because basically government agencies no longer have the monopoly as main data providers for hydrologic and meteorological science and applications. And that requires a way to rethink basically data provision, data access, and also data sharing and maintenance in publicly accessible databases. Now I'm coming to the end of my presentation, but not before showing you a recently published result where we have actually employed microwave links from cellular communication networks for short-term rainfall forecasting, nowcasting, similar to the techniques used with radar. I don't go into the details here because QPF is actually one of the sessions that will be dealt with in the next days of this online conference. And with that, I basically come to the end of my presentation. I would like to thank our sponsors. The collaboration with our National Meteorological Institute, KNMI, is much appreciated. Obviously, also the collaboration with the GSM Association. And finally, last but not least, definitely the contributions of our subsequent PhD candidates. And with that, I thank you for your attention, and I open the floor for discussion. Thank you.
Thanks a lot, Remko, for this quick run through all the different options that we have. And now we also have the option for some questions, and I already see, that Clemens wanted to ask. So I unmute Clemens, who's already in the speaker's room. Clemens?
Okay. Yeah, nice talk, Remko.
Thank you.
My question was, with all this, maybe not, it's not, or my comment is not so valid for the microwave links, but in general for these opportunistic sensing. We cannot control this, and there will be no standard, and these observations will always change. So it means we have always to adapt to it, which takes time. I'm just looking, or if you just look at the weather predictions, or the national centers have to adjust to steadily changing kinds of observations with a lot of variability of errors, which we might not know. And that, what would you say to that?
No, I fully agree with that, Clemens. Thank you very much for your question. And that is absolutely a valid point. And that's also why I'm not claiming that these opportunistic sensor techniques should replace dedicated sensors or sensor networks. As you say, data access is a challenge, which I've also indicated on this slide. There's a huge variability in basically the presence and density of these networks. And also quality control is an important issue. My point is only that basically the infrastructure is there, and we can either use it or not. And so what I'm saying is that we should devote only a small fraction of our efforts to trying to make use of these opportunistic sensing networks. And that is what our group here in the Netherlands, as well as several other groups, notably in Germany, but also in other countries, has been doing for the past couple of years. And basically, the potential of this opportunistic approach lies indeed in those parts of the world where the density and availability of dedicated sensor networks is really low, and that holds for significant parts of the continents, particularly in the global south, but also in the densely populated urban areas where it's often difficult to install in situ networks according to official requirements, for instance, as formulated by WMO. And particularly in those areas, opportunistic sensors, even though we need a lot of work in terms of quality control and a lot of work in terms of convincing mobile network operators or other private parties to share their data, I believe, and together with me, I guess, a whole consortium of researchers, that there is potential enough for this technique to dedicate some of our efforts to these types of sensors. Thank you.
Yeah.
Can I make a comment on this?
Yeah, of course.
No, I must really say, of course, there are networks with a quality which is different from some of the networks we are used to assimilate and to use. But on the other hand, I mean, we already, if you look into the last 20, 30 years, I mean, Siemens knows this, of course, but we already went from fixed stations to airplanes going all over the place, changing all the time, and to satellites with biases which change all the time. And of course, it is another step to go to like very dynamic mobile phone networks or things like this. But on the other hand, we have more and more learning algorithms in this. For example, we have now been able to actually use all the synop measurements now after 20 years. And now it works because we have an adaptive bias correction, and we have this ensemble systems, and suddenly it's a clear benefit. It's no problem, and it suddenly works, and we correct every synop station, and we can even do this with all these private stations. We give them a bias which depends on time of the day, on some other variables, and the system learns the bias for each individual station, and then it just uses it. So after 2-3 days, this is the time scale of the correction of the learning algorithm. Basically, it has picked up the quality, and then it can beneficially use the data. So I would expect that these techniques, perhaps even with some artificial intelligence type learning as well, but also classical techniques. We use classical at the moment for the operational systems, or pre-operational. This is pre-operational at the moment, but there's a lot of potential in that, and so I'm betting on all these new data actually. Yeah.
Thank you very much for that addition. Indeed, that only goes to show that also dedicated sensor networks need careful quality control, as do opportunistic sensing networks. And again, I would like to stress that I'm not at all suggesting that we should get rid of our opportunistic sensing networks, not in the least. Of our dedicated sensor networks, not in the least. Opportunistic sensors are only there, as far as I'm concerned, as a complement to dedicated sensor networks.
Okay, so we don't have time, but we just create some time for some other small questions. So there is one from Rodolfo Alvarado. I don't know if he made it to the speaker's room. No, so I'm asking his question to Remko. What does the parameter A depend on at 30 gigahertz when B is approximately 1? Does it change from one place to another, or how to calibrate it?
Yeah, that is an excellent question. Thank you very much. Of course, if you derive the parameters A and B, so those are the coefficient and the exponent of a power law relationship between specific attenuation and rainfall rate, as shown on this slide on the upper right-hand side for the exponent. If you derive them from drop size distribution observations, as we have done here, the A factor does depend very slightly on the raindrop size distribution, but much less than in the case of typical weather radar frequency. So definitely you would have to adapt that value of A for different rainfall climatologies. We're currently working, for instance, with commercial microwave link data, as I've shown you, from the African continent, as well as from Southeast Asia. And it's very clear there that the rainfall climatology is different, and that has implications for the value of A, but not nearly as much as for typical coefficients of rainfall retrieval relations used in radar metrology. Of course, if you go to practice, then sometimes you can also encounter, or rather often I should say, other sources of attenuation when it comes to the propagation of radio signals between one antenna and the other. So also over here, you should take care of quality control such that other sources of attenuation, notably rainfall or humidity on the covers of the antennas or other constituents of the atmosphere, that you should try to get rid of those before you apply a relationship like this to your received signal level data, or in any case to the difference between transmitted and received signal level data. But in general, the sensitivity of these coefficients to the particle size distribution is much less than in the case of typical weather radar retrieval relations. Thank you.
Thanks, Remko. So Rodolfo already made it to the speaker's room, so he can say if this is sufficient. Or if he's not there anymore, then we have to continue. And one final question from Matt Roberts. I'll just read it out. Interesting talk on opportunistic sensors for QPE. Hopefully uptake of 5G will help, but I think there are some issues between 5G and dual pole radars. Do you know if there are some issues between 5G and dual pole radars? Remko?
I'm not an expert, I must say, on dual pole radars and their potential interference, or the other way around, I should say, of 5G communications. What is an issue, though, and that has received quite some attention in the literature recently, is that actually some of the 5G frequencies overlap with the frequencies employed by meteorological satellites. And so there is definitely an issue there. And I know that the World Meteorological Organization and the American Meteorological Society, for instance, have been trying to convince the US government, which has recently been selling some of these frequencies, trying to convince the US government to make sure that some of these frequency bands will remain for meteorological satellites alone. I'm not sure how successful that argument has been, but definitely it is an issue. On the other hand, you know, this presentation also shows, and I believe also results in the next presentation by Martin Venkel and colleagues from Prague, shows that 5G also has enormous opportunistic potential. So basically there are two sides to this coin, but there are definitely interference issues with meteorological satellites, yes.
Okay, thanks.